Good morning. This is a re-record of the first slide from today's class. The remaining slides will be as recorded during lecture. There's a tech issue on this particular slide. So before I get started, I had reminded the class about, previously on Monday we talked about balancing reactions, how you want the element count on the left and right side of a reaction to be balanced, to be equal. So we're not creating or destroying mass within reactions, merely changing the form of our molecules into the products. We also talked about Avogadro's number. So a mole corresponds to Avogadro's number. So a mole of X is an Avogadro's number of X. Avogadro's number is 6.022 times 10 to the 23. We'll use it today a bunch, but and we'll see some examples of it later too. And then also we had actually looked at this problem last time in lecture 2, so we're going to restart today's lecture by beginning with this problem here. So to calculate a molecular weight in AMU for C2H2, the molecule C2H2, I mentioned that the formula happens to look something like this, which is nothing I expect you to be able to know to sketch the formula, but this is just kind of what the molecule C2H2 looks like. It happens to be called acetylene. You don't need to know that name, but this is just a molecule that happens to be a gas at room temperature. The molecular weight is, the molecule, the atomic weights of 2 carbons plus the atomic weights of 2 hydrogens from the periodic table. So our molecular weight would be equal to 2 times 12.01 AMU for carbon plus 2 times 1.008 AMU for hydrogen. That would be 26.04 AMU. So then the conversion of that into molar mass, I want us to think a little bit about how things convert and how units work from AMU to grams per mole. Let's start with carbon. So let's just take the carbon mass 12.01 AMU, but that's per atom, per one carbon atom. And so for some reason AMU, we don't write the per atom or the per molecule. It's just understood that the AMU is the mass of one molecule. We descriptively write per mole when we mean per mole. So let's convert 12.01 AMU into that unit of grams per mole. And so our AMU to gram conversion, we talked about this last time, but it's 6.022. There's an Avogadro's number of AMU in 1 gram of anything. So 1 gram just corresponds to an Avogadro's number of AMU. And then the atomic weight that we started with, 12.01 AMU per carbon atom. So if we have an Avogadro's number of carbon atoms, that corresponds to 1 mole of carbon. So the molar mass of carbon is 12.01 AMU, divide by Avogadro's number, multiply by Avogadro's number. And so of course that's 12.01 grams per mole. So your masses on the periodic table can be understood as the mass of a single atom on average for that element, or it could correspond to the average mass of a mole of that element. So carbon's molar mass is 12.01 grams per mole, or its atomic weight is 12.01 AMU. Now we can calculate our molar mass one of 2 ways. We could take 2 times 12.01 grams per mole, and then plus 2 times 1.008 grams per mole. Of course, that's the same number, 26.04 grams per mole for carbon, for C2H2. Another approach could be, we showed this last time, is that, well, you can just do the same math here, 26.04 AMU, 6.022 times 10 to the 23 AMU is a gram. And then this is the weight per molecule of C2H2. And then you can multiply by Avogadro's number of molecules. So the molar mass, of course, is 26.04 grams per mole. Now, the idea here is the molecular weight and the molar mass have the same number, yet they're not equal to each other. So the terminology would be the molecular weight is numerically equivalent to the molar mass. So the mass of one molecule, 26.04 AMU, numerically the same number for the molar mass. That doesn't mean the molecular weight is it doesn't mean that the mass of one molecule is 26.04 grams, the mass of a collection of Avogadro's number of those molecules is that molar mass of 26.04. Another thought is sometimes seeing molecule versus mole. These look very similar, but they have different meanings. A mole is a large collection, a huge collection. A molecule is just one. So mol C, like sometimes my handwriting is sloppy, sorry, but if you can see, I'm trying to write molecule and abbreviating it, that's molecule. So let me write this up here. So mole, you could write it out with the E. Usually we write it without the E. So those are representing an Avogadro's number count. Molecule spelled out, or mol C, is our molecule. Looks similar, but different meanings, right? So this is just 1, and this is 6.022 times 10 to the 23. You can look up more digits if you need them, but the 4 sig figs, that's Avogadro's number. And now let's compare the mass of one molecule of C2H2 in grams versus AMU. Well, the mass of a molecule in AMU is 26.04 AMU. The number of grams of one molecule of C2H2, let's just start with number of grams, equals, so we're trying to convert to the number of grams, 26.04 AMU, 6.022 times 10 to the 23 AMU correspond to 1 gram. So let's divide 26.04 by 6.022 times 10 to the 23 gives me an exquisitely small mass of 4.324 times 10 to the minus 23 grams. So a really, really small mass for one molecule. So in AMU, it's a bigger number. AMU is 26.04. But that equals 4.324 times 10 to the minus 23 grams. Okay, so that is our first slide. I'm trying to think if there's anything else I said in class on this slide. I don't think I'm missing anything. I'm about 2 minutes shorter than we covered this in class. But halfway through class, the screen disappeared, and then when I tried to continue, it turned out that my new writing was over top of the old writing that for some reason wasn't being projected into the room. So a little bit of a slide issue here. So the next slide, we'll just continue on with the lecture. Now, let's contrast C2H2 with another formula that looks very similar in kind of concept of what you might think, K2SO4. The only difference between K2SO4 and C2H2 is that we would consider K2SO4 to be an ionic compound. And then when we think of a sample of acetylene, if we have a gas cylinder filled up with acetylene, it's a gas at room temperature. But if we had a gas cylinder of acetylene, we'd have a bunch of individual molecules of acetylene like flying around this container. If I had K2SO4, I'd have a solid that's like a lattice of the negative sulfate ion, 2 potassiums probably on either side, sulfates on either side. I have like a 3-dimensional array of ions. I never really have a distinct molecule. Like you couldn't really look at a K2SO4 sample and find a distinct K2SO4 that's separate from another K2SO4. They'd all be like interchanged together and interlinked together. So you get like a lattice of ions that are all interacting together. So that just leads to a few vocabulary differences. Like there really is no molecule for ionic compounds. So we tend to not have molecules. So this is really not molecular. So therefore, we wouldn't really call K2SO4, we wouldn't say it has a molecular weight. Now, I'll tell you, you will see people calling its formula weight. The formula weight is what you would think the molecular weight would be. It's just the simple summation of 2 potassiums, a sulfur, and 4 oxygens. A lot of people will call that a molecular weight, but it's better termed just the formula weight. So K2SO4 would have a formula weight that just finding it is the exact same process as a molecular weight. It's just not really a molecule. And so the difference would be that you'd have the SO4 2 minus ion, you'd have a K plus ion, you'd have another K plus ion that really aren't connected together through a molecular bond in the same way that they are for acetylene. So acetylene sample, again, individual molecules floating around. So 4 atoms, 2 carbons, 2 hydrogens, another floating around a container separate from each other, K2SO4. All the ions are kind of interlocked together. Okay, so our formula weight for K2SO4 very much the same process. So 2 times the average weight for potassium, so 39.10. 1 times 32 for sulfur, 32.07. And then plus 4 times oxygen is 16.00. So I get 174.27 as the formula weight for K2SO4. But again, the whole idea here is finding it's the same process as it was for C2H2. It's just a slightly different terminology, and that we don't really have molecules within ionic compounds. So you'll see us usually calling things that are ionic formula units. So we usually use the word formula units in place of what you would think of as the word molecule when dealing with ionic compounds. Okay, so just want to introduce that thought. We'll talk a lot about ionic compounds and solubility and stuff as we get into chapter 4 too. So we'll be talking a lot about differences between ionic compounds and molecular compounds as we proceed. This kind of gets back, so this question here is getting at the total number of atoms present within a container of certain types of substances. And we were kind of thinking about this a little bit when we were introducing the mole unit, so we'll kind of come back to this thought here. So if I had a mole of helium, so helium's a gas at room temperature. I like us to just try to picture what, a gas cylinder. So just having a cylinder that is filled up with helium would have helium atoms floating around the container as just individual atomic atoms. Our noble gases are the only group of elements on the periodic table that would exist as monoatomic gases at room temperature. So helium would have helium atoms in this container. And so if we're thinking of our conversion with Avogadro's number to calculate the number of helium atoms, so if we want to calculate the total number of atoms within the container, it's just 6.022 times 10 to the 23, oops, doing it the wrong way. That goes on the top. We want to put 1 mole of helium in the denominator, and that contains 6.022 times 10 to the 23 helium atoms. So whenever I'm thinking I have a mole of this, it's that Avogadro's number of whatever that is. Like helium is just a single atom, so having a mole of helium is a mole of that atom. And so, of course, this is just Avogadro's number. So again, N sub A is Avogadro's number. You could look it up more precisely, but usually for lecture examples, 4 sig figs is good. So again, you could look up more if you need them, but we'll go to 4 sig figs for class. And so N sub A is what I signify as being Avogadro's number. So we would have an Avogadro's number of atoms. We could write out 6.022 times 10 to the 23 as well. But just to simplify writing that number again, so we just have an Avogadro's number of atoms within the 1 mole sample of helium. If I had a mole of hydrogen of H2, again, a pretty simple conversion, but there's some good thought that we can lose if we don't understand that the mole of hydrogen H2 contains 6.022 times 10 to the 23 H2 molecules. So if I have a mole of H2, I have a mole of what that thing is. So that thing is a molecule. So I have an Avogadro's number of that molecule. So Avogadro's number of H2 molecules. Now, 1 H2 molecule contains 2 H atoms. Those 2 atoms within the 1 molecule. So we had done this problem in thought before. Here's just working it out numerically with dimensional analysis so that we can see we get 2 times Avogadro's number. And I think you can see where we're going with this for CH4. We're going to end up with 5 times Avogadro's number, but let's make sure we see why. So again, it's because we have 1 mole. Let me not write 1.0 mole. For every 1 mole of CH4, that corresponds to 6.022 times 10 to the 23 CH4 molecules. And then 1 molecule of CH4 contains 5 total atoms. Now, a few thoughts on sig figs are when we're counting things, those are perfect sig figs. So we don't round to 1 sig fig. Technically, I guess this should be rounded off based off of the 2 sig figs that we start with here. So technically, this would be a 6.0 times 10 to the 23 for 1, 2 times that for 2, 5 times that for 3. So I'm going to keep with the 5 times Avogadro's number here of atoms. And if we're just, at some point we should get off the sig figs thoughts on every single question we do, but we'd be rounding off here to 2 sig figs. I just want to make sure you see that when you're counting atoms, those are perfect counts. Those aren't, sig fig rules don't apply to the things that we count, they apply to the things that we measure. They apply to the inexact quantity. So the only inexact quantity in this problem that we're rounding with is the 2 sig figs and the number that we start with. And again, if we had a number of moles that was like 4 or greater here, we'd want to look up more sig figs on Avogadro's number. We could solve a problem like below. What's the mass of a 0.25 moles of CH4? In grams. It doesn't say in grams, but we'll say in grams so you know what unit to go into. So the number of grams for the sample, we'll start with what we're given. So we have to use the molar mass. I mean, I think we need, hopefully we see that we would want to use the grams per mole because that'll cancel out the mole unit. So we need to, look up the molar mass of carbon. Probably are starting to memorize is 12.01. Most people usually remember it's 12. If you want the extra sig fig, you can look it up. This problem here, 12 would probably suffice since 0.25 only has 2 sig figs. But I just get in the habit of using 12.01 for carbon plus 1.008 for hydrogen times 4. So that's 16.04 grams. So I'm getting this, of course, is from the periodic table, summing up 1 carbon plus 4 hydrogens. So that gives me 4.0 grams. So a quarter of a mole of CH4, 4 grams. A whole mole, 16 grams. A mole of water, 18 grams. So 18 grams of water would correspond to a mole, and that would correspond to an Avogadro's number of water molecules. So formula weights, we can calculate from formulas like mass percentages. So if I give you a formula, I can calculate the percent by mass that's carbon or hydrogen in a molecule like C2H2, or maybe a different molecule, C2H6. Now for C2H2, C6H6, they share the empirical formula, the simplest ratio of their elements of CH. So they both have that empirical formula of 1 carbon ratio to 1 hydrogen. And let's see what role that plays in the percent by masses. So if I start with CH2 and calculate the percent carbon in the molecule, the percent by carbon would be equal to the mass of carbon in that molecule. So if I look at 1 molecule of C2H2, I have 2 times 12.01 AMU due to the carbon. You can go AMU or grams per mole here, it doesn't make any difference. Just use the same unit for the count for carbon versus the count for the whole molecule. And so then what I want to look at is the formula weight of the whole molecule of C2H2. And so we previously did that number, if you remember on the other slide. Earlier was 26.04 AMU was the formula weight for the whole molecule. So we take just the carbon mass in the molecule, divide by the total mass of the entire molecule. So 2 times 12.01, divide by 26.04. That gives me 92 let's go to just, we'll go to 3 sig figs here. So we'll call it 92.2%. So that's the percent of the mass in C2H2 that's due to the carbon in the sample. The percent by hydrogen where the percent of the mass that's from hydrogen is just either the difference, so you could probably guess that it would be 7.8%, but we should get that number to work out by taking 2 times 1.008, the mass due to hydrogen, divide by the formula weight of the compound. Oh, there's a times 100% in here that I didn't write above. So we're multiplying by 100% to take the fraction into the percentage. So we're taking the fraction and then just multiplying by 100. So 2 times that mass of hydrogen, divide by the formula weight, times the 100 to get it into a percentage. So I get 7.7%, my rounding. If I went an extra sig fig, let me go 7.74. I guess to write this as 3 sig figs. If I went back to the 92.2, it was like 92.25 or 24, so they would still sum up to 100. So I was maybe prematurely rounding just to make sure we see the proper rounding, that these should sum up to 100% within a little bit of rounding error that we see, like in this example here, we're off by like a tenth it looks like, but that's just from simple rounding errors of not writing an extra digit or two here, or not even including an extra digit or two in the formula weights. But the key detail I want to see is if we look at C6H6, that we're going to get the same numbers here. So 92.2%, 7.74%. Let's look for C6H6 and see that, of course, we're going to get the same percentages out as we did for the compound it shares an empirical formula with. So for the percent carbon in this compound here, 6 times 12.01 AMU. Now the formula weight we have to use for C6H6 down here, that would be 12.01 times 6 plus 1.008 times 6. That's 78.11. And I get that 92.3%, slightly off on my rounding here, but let me actually call this 92. Let's give the extra digit so we're not seeing this as a slightly different number. So this would be 92.25%. And let me rework the previous one for C2H2. It's 92.24%. So the difference of 0.01 here is just the rounding errors that we could have gotten rid of if we just were a little bit more precise in our atomic weight. So in other words, the percent by mass of compounds that share an empirical formula are the same as each other. They're equivalent to each other within small rounding errors or small experimental errors. So the percent by hydrogen would be that difference for the C6H6 as well. We won't go through the calculation for the percent by hydrogen in C6H6. It would be that roughly 7.74 to 75% mass by hydrogen. Now what this is telling us is then if we give you percent by mass data, because that's going to be an example in a couple slides from now, if I give you percent by mass data, can you find an empirical formula from that? Yes. Can you find a molecular formula from that? No. So we're going to see that if you want to find for an unknown sample, because this is like an important question, I think, is like how do we ever determine what a formula for a compound is? What we're going to see is that, well, you might determine mass percentages of the elements to get an empirical formula, and then find a way to get a molecular weight to work out what the molecular formula is. So we'll see that there's like a two-step process for finding a molecular weight and a molecular formula for a compound in a couple of slides from now. Okay, so compounds that share an empirical formula will share the same mass percentages. Therefore, if you only know the mass percentages of an unknown compound, all you can ever determine is the empirical formula. Now, there's a lot of conversions we can use with Avogadro's number, with formula. So this slide here is just kind of showing us that we can go from grams to moles for a sample. To go from grams to moles, you need a molar mass. To get a molar mass, you need a periodic table. So you take periodic table, you know what the molecule is. If I give you a certain amount of mass of water, you can convert that into moles of water. You just need the molar mass, therefore you need a periodic table. If you want to go from moles to particles, do this conversion to moles to like molecules in the sample, moles to the atoms in a sample if it's like a noble gas sample. Here you need the formula. So if you inspect the formula, you can determine, here you need Avogadro's number to make this conversion. So here we need Avogadro's number to go from moles to particles or to molecules or to the count of particles within the sample. This is Avogadro's number. Then if we want to go to atoms, like we were doing earlier, this is where you need the formula. So you need to inspect the formula to figure out the count for each of the atoms or for the total molecules like we were doing in the H2 and the CH4 example previously. Okay, so we can interchange and interconvert between these units as long as we know what formula are, what Avogadro's number is, and then how to use a periodic table. So we'll go through an example with water where we have a 100-gram sample. So can we calculate the number of moles of water in this sample? If so, what do we need to know? Can we calculate then the number of water molecules present? If so, what do we need to know? Can we calculate how many hydrogen atoms are present? How many grams of hydrogen are in the sample? Why don't I give you guys a minute or two just to start the first problem or two, and then after a minute or two, I'll start to kind of catch us up and kind of see where we're going. Let's just make sure we can get started on these kinds of problems. And if there's anything you're confused about, you can double check with your neighbor, talk, do whatever you want to do for a couple minutes here. All right, let's walk through a couple of these steps here. So you guys hopefully had kind of gotten the 100 grams to moles just by using the molar mass of water. And just, if you weren't sure, you were looking at the periodic table to go 2 times hydrogen's mass plus oxygen. So that's 18.02 grams per mole. So just over 5.5 moles of water are present within the sample. We then, to convert to the number of molecules, just need to use Avogadro's number. So we take, for every 1 mole of water, we would have an Avogadro's number of water molecules. So we just need to take 5.549 times Avogadro's number. I don't know if any of you guys are on the iPhone, but my iPhone is not kicking into scientific notation mode. So I had to count all the way over to to get times 10 to the 24. For the life of me, I cannot figure out how to get this to switch into scientific notation. I've never seen such a big number on the screen before. That's silly. Like a year ago, they updated the calculator on the iPhone and ruined it. I don't know how you can ruin a calculator, but they did. Does that number match anyone else that calculated it? Okay, just making sure I didn't read it wrong. Okay, so the next step is calculating the number of hydrogen atoms present. So we take the number of water molecules. So in that 100-gram sample, which is about 100 milliliters of water, so just a relatively small amount of water, we have over 10 to the 24 water molecules, such a huge number of molecules. It's almost inconceivable how many molecules that is. But for every 1 molecule of water, just from inspection of the formula, we have 2 H atoms within the formula. So it's just saying that there's 2 hydrogens for every 1 water molecule. So the total number of H atoms, now this isn't free hydrogen. The hydrogens are still attached 2 to 1 to oxygen. So they're not free H atoms, but the total number of hydrogen atoms bonded to water here in the sample will be 2 times that number. So that's 6.684 times 10 to the 24 H atoms. And then how much of that mass is hydrogen? Like how much of the mass of the water sample is hydrogen? There's a few ways we can approach this problem. Let's do this 2 ways. So approach 1 can just continue from the collection of hydrogen atoms that we calculated in the previous step. So 6.684 times 10 to the 24 H atoms. That we could just address the question, can we figure out the mass of that collection of hydrogen? And we should be able to. We just have to maybe either convert to the mass in AMU and then convert AMU to gram, or maybe convert molecules back to moles and then use a molar mass for hydrogen. And so I'm going to use the Avogadro's number conversion first. So I'm going to take an Avogadro's number. If I take for every 6.022 times 10 to the 23 H atoms, that would correspond to 1 mole of hydrogen. And now, sometimes you get confused here of thinking, is it a mole of H2? Is it a mole of water? Is it a mole of whatever? It's a mole of this. So I go, at Avogadro's number of that is just a single atom. So an Avogadro's number of the H atom is a mole of the H atom. So a mole of hydrogen, Avogadro's number of hydrogen atoms. And then we can just use the molar mass of hydrogen from the periodic table. It's 1.008 grams per mole. So 1 mole of hydrogen, 1.008 grams. So if I divide my previously calculated H atom count by 6.022 times 10 to the 23, that's the moles of hydrogen present in the sample. Now, if you hit enter on that screen, the moles of hydrogen in the sample is like double the moles of water. So if you think back, we had 5.5 moles of water times 2, about 11 moles of hydrogen in the sample. And then the last step times 1.008 grams. So that huge count of hydrogen only corresponds to a mass of 11.2 grams. Call it 11.19 grams. So the water sample, 11.19 of the grams are hydrogen. The remainder is due to the oxygen. Now I mentioned I do this 2 different ways. So So a second approach or an alternative way to find the mass of hydrogen, there's probably even more ways than two to find this, but another approach could have been just to start with a 100-gram sample. So the mass of hydrogen in the sample, you could take the sample mass, the 100 grams, and just multiply it by the percent of hydrogen by mass. Now, sometimes when I zoom out, it makes the whole screen disappear. So we'll see, hopefully. I don't know why it disappeared earlier. And now I've been really worried anytime I touch my screen, half my handwriting is going to disappear. So we could take the sample mass, just multiply the percent by mass, it's hydrogen. So the percent by mass of hydrogen, if you recall, would just be inspecting the formula. So we just go back to the formula of water, 2 times 1.008. You can go grams per mole or AMU, doesn't matter. Let's say AMU. And then let's divide that by the formula weight of water, which would be 18.02 AMU. You can either multiply by the 100%. The percentage math sometimes confuses us. If I multiply by 100% and then multiply a number by the 100%, the number is really the fraction still. So like if you multiply like 100 times 80%, it's still 80. Like 100 times 0.8 is 80. It's not like 8,000. So like don't let the percentage confuse you. So I'm going to put the 100% here. And then I'm probably going to just like ignore it from the calculation because a percentage doesn't really, I don't really multiply the result by 100 unless I want to give the result with a percent sign. But if I'm just trying to take the fraction of the mass of water that's due to hydrogen, I can just take this percentage and then multiply by that 100-gram sample that we started with up here. So in other words, if I take 2 times 1.008, divide by 18.02. If I hit enter, I see 0.1119, some other numbers, but that's 11.19%. What I'm saying is you can either multiply by 100% and know that's a percentage and then do the proper percentage where it really is the fraction, or just leave it as the fraction. So whether or not you actually multiply by 100 here is irrelevant because if you do, it's a percentage, and then you need to divide by 100 when you get your answer, or you can just like keep it as the fraction. But I just want us to see that you can take the percent by mass and multiply the mass percentage into the 100-gram sample. So multiply that by a 100-gram sample, then 11.19 of the grams are due to hydrogen. And if you do the problem and you end up with 1,119 grams, obviously we don't have over the sample mass of hydrogen in the sample, and it's just due to 100% is really a fraction. So like you multiply by the percent, keep it as a percentage, so it's really the fraction, and then multiply that by the 100-gram sample. And so then this mass here is just from the sample mass that we started with. Okay. I'm now feeling like the second approach is more confusing than if I hadn't even done it. But it's just going back to what a mass percentage is. So if I know what a mass percentage is, I should be able to multiply that by the sample mass and get the percent of that element. Okay, so let's look at this question here. Let me throw this to you guys too. So how many nitrogen atoms in total are present within a sample of 4.72 grams of magnesium nitrate? We tend to, like, as we proceed, we really don't get to review nature. Like, we don't throw you a lot of nomenclature on like midterm 2 to retest you on nomenclature. We will look at the exam being cumulative for the final. So the final exam will be cumulative. Our midterms, generally, we'll give you the formulas and the names so that you don't get caught up on nomenclature. So we are given the formula here too. So see if you can calculate the number of nitrogen atoms in the sample. Take a minute or two. I'll start writing in about a minute if you want to get a little help, and then I'll walk through the answer after that. Okay, so I don't know if you guys were making good progress here, but just to catch up, or if you were stuck. So we start with our mass that's given. We calculate the formula weight for MgNO32. It's an IC. We might call it a formula weight as opposed to a molecular weight, but 148.3 grams per mole is what I got for its molar mass. Now this step here, I can think of this step in two different ways. One way is shown here where I can think a mole of magnesium nitrate, since there's two N's in the formula, would have 2 moles of nitrogen present. So for every 1 mole of the molecule, I get 2 moles of nitrogen. That's one way I can think through the problem, and then think 1 mole of nitrogen contains an Avogadro's number of nitrogen atoms. So an alternate approach, some of you guys may have done this slightly differently. You could have said, for the second step, you could have went 1 mole of MgNO3 contains an Avogadro's number of MgNO32 molecules, but that's, like we said earlier, not really the right terminology. We might say units, but units is just kind of like a molecule. It's just like that collection, like a unit is, like we could say like a molecule is a unit. It's just like the molecular unit. Here, this is like the ionic unit. It's just that collection of atoms. So a unit would be 1 magnesium and then 2 nitrate ions. And so then from there, you could say that 1 unit, so 1 MgNO32 unit contains 2 N atoms. So you see it's the same math. So we're multiplying by 2 in Avogadro's number. It's just a matter of, do you see it for 1 mole of the compound, 2 moles of N, 1 mole of N to Avogadro's number? Or do you see it to Avogadro's number of units, and then each unit contains 2 nitrogen atoms? So the math works out the same either way. So I get answer C. Is that what you guys got too? Or if anybody who made it through. It's a pretty long problem. You may not have made it through. Okay. So the key is like getting the vocabulary down. The other key is like canceling our units. And I don't always do this. Sometimes it's really useful to make sure that we're seeing that our units here are canceling and we're getting towards what it is that we're looking for. If you find dimensional analysis that you get stuck, ask yourself, did you forget to write the units? I see this a lot. Like writing the units in a dimensional analysis step is almost required to ever be able to get the right answer. So if we're going to eventually do stoichiometry. You guys remember that's mole-to-mole conversions of problems. If we neglect writing units, we're going to get stuck in problems all the time. We're going to invert numbers that we shouldn't invert. If you're dividing by Avogadro's number where you should be multiplying by Avogadro's number, probably a unit issue. If you just follow the units and track them through the problem, I guarantee you'll have better success at getting towards the right answer. So if you weren't writing in the units and canceling them out, if you just had the numbers, the units are so helpful to making sure that when we take a test that we have things in the right spot and we get the right answers. Okay, so the middle part of the chapter is then like, how do we determine these formulas? So like section 3.5 in the textbook is all about, well, if we give you mass percentages, can we get back to a formula? And what we're showing earlier with the C2H2, the C6H6 example, is that the best you can do with the mass percentages of the elements in a substance is an empirical formula. So if you get percent of this element, percent of that element, you can get the simplest ratio of the elements in the formula, the empirical formula, but then we're going to need a molecular, to get the molecular formula, we're going to need a molecular weight determination. So the two things that we'll see is that percent by mass data is relatively easy to determine with lab experiments. So we can get percent of the elemental composition of a sample very easily. And we can also do a mass spec experiment to get a molecular weight pretty easily. So we'll see a 2-step process for finding a molecular's formula and then getting its molecular weight from a mass spec example to get its molecular formula. All right, let's take our quiz for today. And I feel like I've pressed your brains enough for today, so let's wrap up with this quiz here. So once you get your attendance marked, keyword today is glucose. So let's finish get some glucose and get on to our next classes. So we'll wrap up here for today.